All right, lesson 9, the product rule. So in this one, what we're going to be doing is figuring out the derivative of some function times some other function. So maybe something like this, right? 4x to the power of 3 times 5 minus 3x. And right off the bat, you might be saying, yeah, why can't we just do what we did in the last one, though, and just expand this out and then take the derivative of those two terms that would be left? And yeah, you could. And to tell you the truth, that probably would be the easier way. And once we start doing a lot more of this, I tend to lean on those ones because it would be easier. But sometimes it doesn't actually work out. Sometimes you actually have to, like let's say if this was like the square root or something, right? I can't just expand that in. So we need a general rule for multiplying these guys. All right. So the question here is saying, if we have this function, is the derivative of the function equal to the derivative of 4x to the power of 3, so this one, times 5 minus 3x, which is times this one. So can I just take the derivative of this, and then multiply them to get the derivative of the whole thing? And it turns out that no, you can't. So I'm not going to go any more into that. I'll say no, it doesn't actually work out. But we can't. Let's develop an actual rule for differentiating functions like this, okay? And we're going to base it on first principles, right? The limit as h approaches 0 stuff, because that's where it all comes from, okay? So let's take this general f of x is equal to a of x plus b of x, two functions multiplied together. So we'll say, all right, then f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x over h, right, which is our general equation there. And now let's kind of fill in what we actually have, though. So what we're dealing with is it would be a of x plus h times b times, let's write different, times b of x plus h. Now, I know this looks a little bit confusing because those look like brackets, right? But this is really a of x plus h times b of x plus h, right? Those are functions. All right, so then minus, and then it would be a of x times b of x. And then that's all over h. All right, so now what we're going to do, we're going to try to manipulate this guy. We're going to play around with this one. And what I'm going to do, I'm actually going to, well, here, no, let's write it out. So this is what I'm going to do. We're going to say this is equal to the limit as h approaches 0 of, and then I'm going to write this again, but I'm actually going to introduce a term. And I'll explain why I'm doing it in a second. So this would be a x plus h, just writing it all again, b x plus h. Okay, and then in the middle here, though, I'm actually going to introduce a minus. Here, I'm going to make this a different color so you can see what I'm doing. So it'd be a minus a x plus h times b of x, okay, just this term. And then I'm going to add that exact same thing. So it'd be plus a x plus h and then b of x. Okay, just bear with me. I'll explain this in a second. And then minus a of x plus b of x. Okay, so what I just did there is really nothing, right? I subtracted a of x plus h, b of x, and then I added it, right? So that was 0. I didn't actually introduce anything, right? I just did it and took it away. But the reason why I did that is because now we can actually do something like we can do some factoring by grouping here, right? I can factor some stuff out of this, and I can factor some stuff out of this to make it kind of work out. Now you might be saying, why did you specifically do this, right? Why didn't I do like minus b x plus h times a of x? And the answer is I could have. I could have actually wrote it the other way, and it would have worked out to give me the same solution. So I just did this one for now. But all right, so yeah, this is what we're going to do. We are going to look at this chunk of it, and we're going to factor out what we can. Okay? So this would be equal to the limit as h approaches 0 of, and then you can see I have a of x plus h, a of x plus h, I'm going to factor that out. Okay, so that would be a of x plus h. And then I'm going to make a square bracket just so I can differentiate here. Differentiate. Sorry. Okay, so then that'd be times, so b of x plus h still. Okay, and then you'd still have minus and then this b of x. All right, so that was that first part. Now moving on to the next one. So now we'll look at this chunk. This chunk in green. Okay. All right, so then we're going to have plus, and then what do we have in common on this one? Well, we have b of x in common. Okay, so then we have b of x, and then again I'll use a square bracket, and then what we have left is a of x plus h, and then minus, and then you still have a of x left. All right. Oh shoot, and we should have, both times we should have said that this was all over h, right? All over h, all over h. Now what we're going to do is we are going to split this up where right now it's everything over h, but that really is the same thing as this term over h and this term over h. So let's write it that way. So we'll write it as the limit as h approaches 0 of a of x plus h times b of x plus h minus b of x over h plus, and now we can take the limits individually too, right? So this would be the limit of h of 0, or h as h approaches 0, sorry, of b of x times a of x plus h minus a of x all over h. Now we can split this up even further, and we can say the limit as h approaches 0 of, and I can just take the limit of just this chunk and then just this other chunk, right? Take them on their own. So we'll say the limit of a of x plus h, okay, times the limit as h approaches 0 of everything left here. So that would be b x plus h, well, didn't turn out, minus b of x all over h. And I promise this is all going to make sense here in a second. It's all going to work out why we're doing this. So then we're going to say plus, and then again we're going to do this. We'll do the limit as h approaches 0 of just b of x. Okay. And then times the limit as h approaches 0 of, and then everything that's left there, right? So that would be a of x plus h minus a of x all over h. All right. Now the reason why we did this is because let's see what's going on here now. So if we actually take the limit as h approaches 0 of this first one, right? So that means I can throw a 0 in there. This would become a of x, right? That's what the limit would be in that case, right? So that'd be the limit is a of x for that one. And then it'd be times. Now, this chunk here seems like, okay, I got nothing to do with this. Like, how can I figure this one out? But this actually is the same thing as b prime of x, right? That actually is the derivative of b, right? That's the definition of a derivative right there, okay? And then plus, and then moving on to this one, well, there is no h even in this one to take the limit, so this would just be b of x. And then the second part here, this is actually the definition of the derivative for a of x, right? So this would be times the derivative of a of x. Well, that's pretty neat. That is our derivative, right? That is the definition of the product rule, which we're going to show in a second. And what this means here, like 1d2 plus 2d1, It's just a way of kind of remembering this, right? Like the function 1 times the derivative of 2, function 2, plus 2 times the derivative of 1, right? It's just kind of like just a way of remembering this equation. So yeah, this is our derivative rule, right? And this is formally how it's stated. So Leibniz notation would be the bottom one, right? So let's even look at that too. So these would be with the prime notation, right? So the derivative of f times g, so that'd be prime for the both of them, would be equal to f times the derivative of g plus g times the derivative of f, right? And Leibniz notation is d, so it's quite often written like this, d dx, and then you put in brackets what you're taking the derivative of. Okay, so that'd be like, it's on the top there, right? It's like dy dx is what that was before. But the y in this case is now all of this, right? Okay, is equal to f of x, right? The original function times d dx of, gx, the derivative of g of x, plus g of x times the derivative of f of x. So that means the same thing, but maybe just a little bit more confusing looking. Yeah. All right, so let's do this one. So let's write down our equation so I can see it on the screen here. So it's the derivative of f times g is equal to f times the derivative of g plus g times the derivative of f. Okay, so let's give these names. So let's call this first chunk here, that would be f. Okay, and this would be g. All right. So now y prime, this one won't be too bad, right? So this would just be, well, f. All right, sorry, I had to leave there. I don't know where it was at. Let's start over. Okay, so it's y prime is going to be equal to f, so just the function f. So that would be x squared plus 2, okay, times now the derivative of g, right? So I'm looking at g. That's an easy one to take the derivative of. That would be 3x squared. And then that would just be minus 5, okay? So we've done the first part. And then plus, and this would be g, so x squared minus 5x, and then times the derivative of f. So that would just be 2x plus 2. Now, that is the derivative, right? If you put all that in, that would be the slope at whatever point you were looking at. But now, yeah, that's not nice to look at, is it? So we would want to expand that out. So we'd say y prime is going to be equal to, so that ended up being, 3x to the 4 minus 5x squared plus 6x squared minus 10 plus 2x to the 4. Ooh, okay. I hope I said 3 there. Looked like a 2. Okay, so 2x to the 4 minus 10x squared. Okay, and then just collecting like terms, you'd say y prime is equal to 5x to the 4 minus 9x squared minus 10. And there you go. So now I showed you how we can do this using the product rule, right? Tell you the truth though, I think a lot easier way if you didn't have like square roots or something like that involved, like where you couldn't actually multiply it out, it would have been easier to FOIL this guy and then take the derivative of the product, right? And that would have worked just as well too, right? So, but like I said, we're going to run into situations where we can't do that, so this is good practice. All right, next one. So again, it'll be the derivative of f times g is equal to the derivative, or f times the derivative of g plus g times the derivative of f. Okay, so this is f and this is g. So we'll say the derivative of f of x is equal to, and then you know what? We are going to write these as exponents. Actually, let's do that first. Sorry, let's go back. So let's rewrite this. So f of x is equal to, and this would be x to the 1/2 minus 2x times 3 minus x to the 1/2. Okay, that'll just make it easier to take the derivative now. All right, so f prime of x is equal to, and then this was f and this was g, so this, just write this one again. X to the 1/2 minus 2x, and then the derivative of g, so this would be negative 1/2 x to the negative half, and then plus, and then g was just writing that again, 3 minus x to the 1/2, and then the derivative of f, which would be 1/2 x to the power of negative 1/2, and then minus 2. Okay, simplifying this up, we have f prime of x is equal to, now, so this will be this term distributed into both, right? So this would be negative 1/2, and then x to the 1/2 times x to the negative 1/2, those actually cancel. So this is just negative 1/2, and then plus, and then the next one here would end up being x to the 1/2, right? Because this would be negative 2 times negative 1/2 would be 1, so there's nothing out front. And then this is like x to the 1, so 1 minus 1/2 would be 1/2, right? And we don't really need that bracket there because we're expanding it all out. Now on to the next one here. This would be minus 6, right? Sorry, my bad. That would be plus 3 over 2 x to the negative 1/2, and then minus 6 minus 1/2 plus 2x to the 1/2. Okay, and then simplifying that all up one more time, we'd end up with 3 root x, right? Just any x to the 1/2, right? I'm just calling that root x now, minus 7 plus 3 over 2 root x. And that part just comes from this, right? Like 2 and then root x on the bottom would come from right there, right? Okay, next one. Suppose f of 3 is equal to 4, and f prime of 3, or the derivative of f of 3, is equal to negative 1. And it says g of 3 is equal to 2, and g prime of 3 is equal to 2. Find f times g prime of 3. All right, so f times g prime at 3 would be equal to, and it's f, so we'll say f of 3 times g prime at 3 plus g at 3 times f prime at 3. Okay, this really just is the equation above, but we've just specified this at the x value of 3 for every one of them, right? And the good news is we know all these things, right? Like everything we have going on here is what we were given. Okay, so we can actually just replace those with the numbers that we know. So f of 3 is 4, right? So this would be 4 times, and then g prime of 3 is 2, plus, and then g of 3 was 2, and then f prime of 3 was negative 1. So that's equal to 6. All right, last one. This one says, find the equation of the tangent line to the graph of the function this at the point where x is equal to negative 2, and then write your answer in general form. So we've actually done a few of these now, right? So this is the only difference is that we're just multiplying now. So let's do what we've always been doing. We'll find the derivative. So y prime is going to be equal to, well, you know what? Actually, let's just rewrite y one more time, just make it look a little bit nicer to take the derivative. So we'll write this as y is equal to negative 6 x to the negative 3 times, and then 2x minus 9 x to the negative 1. And this is my f, and this is my g. Okay, so now y prime. So y prime, so it's going to be, here, let's write that down too. So it would be f times g prime is equal to f prime times, no, f times g prime plus g times f prime. All right, so f, so we're just going to write this down again. So this would be negative 6x to the negative 3, just writing down f again, times, and then the derivative of g would be 2 plus 9x minus 2, plus, and then the derivative of f, or we'll do it the way it's written. Either one would work, but we'll say 2x, just writing it again, 2x minus 9 x to the negative 1 times 18 x to the negative 4. Okay, just the derivative of f there, okay? Okay, and then simplifying this, we get negative 12x to the negative 3. Okay, just distributing that out. Minus 54x to the negative 5 plus 36x to the negative 3 minus 162x to the negative 5. And then just collecting like terms, we get 24x to the negative 3 minus 216x to the negative 5. Okay, so now we will throw in our value, right? Because we want to know what the slope was at negative 2, right? So there's our derivative. So if we throw in negative 2, we should be able to figure out what the slope is. So the slope, which is equal to y prime, would be equal to 24 times negative 2 times to the power of negative 3 minus 216 times negative 2 to the power of negative 5. So putting all that in, we end up getting 15 over 4 for our slope. Okay, so remember what we're after here, right? We want an equation. So we want y minus y1 is equal to mx minus x1, right? And now we have the slope. We're good there. And we already have x1 too, right? That's going to be that point, right? Because we know this point's on the line. The only thing we don't have is y1. So let's figure out that one. So just back into the original equation, we just got to figure out when x is negative 2, what y comes out as. So we'll say, so find y. Okay, so y would be equal to negative 6 over negative 2 to the power of 3, and then 2 times negative 2 minus 9 over negative 2. So putting all that in, we end up getting 3 over 8. All right, so we are almost there. So now we'll throw it in. So we'll say y minus, and then y1 was 3 over 8, is equal to 15 over 4 for our slope, and then x plus 2. All right, so now it wants it in general form though, so we don't want any fractions, and I got to get rid of the brackets too, but this might be just a good place to get rid of the denominators right now. Why don't we multiply everything by 8, right? So I'll multiply this by 8, this by 8, and this by 8. Okay, so that 8 cancels with that one, and this becomes 2 up top. Okay, so let's rewrite this as 8y minus 3 is equal to 30x and then plus 2. Okay, and then I'll distribute. So we got 8y minus 3 is equal to 30x plus 60. And then with general form, we want a positive y or x value. And it goes x, y, and then the constant. So I'm going to bring everything over to the right because it's already positive. So bringing that over, we get 30x minus 8y, and then add 3 to both sides, so plus 63. And that was all equal to 0. All right, so that's how you do that one. Again, though, maybe I'm saying this too much. At this point, right, this was our original function here. Again, I think it probably would have been easier if we were doing this for practical purposes to distribute, right? We could have distributed that right off the bat and then taken our simple derivatives. That would have been like a lot less. It would have avoided this, right? Kind of stuff. But again, we won't always be able to do that. So this is good practice, right?